so today we're going to take a look at our second lesson in Geometry Concepts, lesson 1.2, which is inductive reasoning. So our goal for this lesson is to use inductive reasoning to make conjectures. So the first thing we're going to do is take a look at some of the vocabulary. So the first thing we're going to take a look at is defining conjecture. So we're going to make these conjectures. We need to know what they are. So the definition of a conjecture is an unproven statement that is based on a pattern or observation. All right, so that's our definition of conjecture. I'll make this a little bit larger for you to see. I typed that because I don't have the best handwriting. So this is what a conjecture is. It's just an unproven statement that we're basing on our patterns or observations. Inductive reasoning, when we use this inductive reasoning, we're looking for patterns and making conjectures is part of a process called inductive reasoning. So when we look for patterns in things, kind of like when we were playing two truths and a lie, I was looking for patterns and I made conjectures. I made a guess. And that was called using inductive reasoning. And so the last word we're going to define has to do with our counterexamples, and that's going to be our last couple of examples. But a counterexample is an example that shows a conjecture is false. So when we say all math teachers are boring, Mrs. Woodard is a counterexample to that, because for sure I am not boring. All right, so let's take a look at how we use these conjectures, how we make these conjectures. So we need to complete the conjecture. So our first conjecture is the sum of any two odd numbers is. We need to decide what that's going to be. So make sure we know the meaning of the conjecture. So a sum is the answer to addition. So that means we're going to be adding two odd numbers. And odd numbers are 1, 3, 5, 7, 9, or any number that ends in one of those 5 digits. So to make our conjecture, we're going to have some patterns that we look at. So we need to have examples to form those patterns. So they give us some random problems to try. So they say 1 plus 1. Got that one down, it's 2. 3 plus 13. Hopefully you can do that rather quickly without a calculator. That's 16. 5 plus 1 is 6. 21 plus 9 is 30. And 3 plus 7 is 10. One last one, a good test of your mental math. 101 plus 235 is 336. So if we look at each of those sums, what do they have in common? Well, there's 1-digit numbers, 2-digit numbers, 3-digit numbers. So the number of digits doesn't matter. We're looking at what type of number it is. The sum is even in all of them. So we can make the conjecture. So the answer to our question, the sum of any two odd numbers is even. And so that's what it means to make a conjecture. We look at the examples and decide what do they all have in common. So, which of the following reasoning stages were we using in that example 1? Well, we looked for a pattern. So we were looking for the pattern. And then after we looked for that pattern, we didn't verify the conjecture, we simply made a conjecture. So we looked for the pattern, and then we made a conjecture. All right, so example number 2, once again, we're still making conjectures. So the sum of the first n odd positive integers is. So we need to figure that out. So our solution here is the variable n, which they put up here, this variable n, refers to the number of odd positive integers that we've added together. So that value, because it's a variable, is going to change. So we may have 2 odd integers added together, 3, 4 added together. So let's put this in a split screen and put it side by side and take a look at that. So we're going to list some examples and look for the pattern. So if we have one odd number, the sum is just 1. So 1 equals 1 equals 1. And if we take, which is 1 squared. If we take a look at the first 2 odd numbers, the sum is 1 plus 3, because those are the first 2 odd numbers, which is 4, and that's equal to 2 squared. If 3 is our n value, so we're adding 3 of these together, we get 9. 9 just happens to be 3 squared. 4, 1 plus 3 is 4, plus 5 is 9, and 9 plus 7 is 16. That 16 just happens to be 4 squared. So hopefully you're using your inductive reasoning and starting to see this pattern already. But we know that these 4 add to give me 16, and 16 plus 9 is 25. And yes, it did follow through that we get 5 squared. So for any n value that we give you, the sum is going to be n squared. So the sum of the first n odd positive integers, so we have a lot of requirements here, is simply n squared. All right, so the follow-up to it. This is going to be one that we check in class, but you're going to use that conjecture you made, that if n is equal to 8, what the sum should be, and then you're going to check that. So this is going to be one of those that I would call a check in class problem. I'm expecting you guys to do that one on your own. So you can pause the video or go back to it when you get done watching. All right, here's your first checkpoint. I know it's a little bit dark here on my screen, but you guys are obviously using your book, and then we'll check this in class tomorrow. But you're going to complete the conjectures based on these patterns. So you're going to tell me what the product of any 2 odd numbers is, and then what the product of n minus 1 and n plus 1 is. So we'll take a look at those. Once again, we're calling this our check in class. These are what we'll be checking. So they're done tonight, and we're checking them tomorrow. All right, so now we're moving on to the third examples. We're finding counterexamples. So what we're trying to do now is prove someone's conjecture false, which we all enjoy doing, is proving someone wrong, by finding the counterexample. So the sum of 2 numbers is always greater than the larger of the 2 numbers. So here we are. We're going to come up with an example. So here's a counterexample for that. Let the 2 numbers be 0 and 3, the sum of which is 3, which is not greater than this larger number, 3, which is the larger of 2 numbers. So because your answer was only equal to your largest number, we know that our conjecture was false. All right, so now what you need to do is you're going to use that same conjecture that the sum of 2 numbers is always greater than the largest number, and make a counterexample for that. So here's another checking class problem. All right, example 4. Show a conjecture is false by finding a counterexample. All shapes with 4 sides of the same length are squares. 2 counterexamples are shown at the right. These are all have 4 sides of the same length, but they are not squares. These are what we would call a rhombus or a diamond. So our conjecture, once again, is false because we found these counterexamples. I have 4 equal sides, 4 equal sides, but they are not squares because they don't have the 90-degree angles. And so here is your last checkpoint. Show the conjecture is false by finding more counterexamples. So if the product of 2 numbers is even, then the numbers must be even. So you need to find a product, which is the answer to multiplication that is even, but one of the two numbers was not even. And then if a four-sided shape has two sides the same length, then it must be a rectangle. So you need to come up with an example, a counterexample, or a diagram for that. That's the end of our notes. Once again, the checkpoints will be our checking class problems. I hope you've enjoyed your second video for Geometry Concepts.